In this exercise, we're given W is the span of these two vectors, and we're in the space R4, and I mean the inner product space, because in this chapter we're not just dealing with vector spaces. And usually I won't say, and if I don't say, it means the standard inner product, which is the dot product. Okay, there's two questions. One is to find a basis for W perp, that's the orthogonal complement, and its dimension. And in the second part, to show that the result from the first part confirms the orthogonal decomposition theorem. Now a vector, say x, y, z, t, will be in W perp if and only if it's orthogonal to all the vectors in W. But we don't need to check it against all the vectors in W. It's enough just to check against these two because they span W. If something is perpendicular to these two, it will be perpendicular to any linear combination, i.e. to all W. So let's write down those two conditions using set theory notation. W perp is the set of all x, y, z, t such that something and something. This says that it's perpendicular to this vector because the inner product is the dot product equals 0. That's the condition. And to be perpendicular to this one means the dot product with this, which is the inner product, is 0 also. Now this dot product, you just take the first with the first and multiply the second with the second, the third with the third, and so on, and then we add them together. So it's 1 times x plus 2 times y. So what we get is this. And similarly, this dot product is 2x and so on, gives us this. So what we have is a system of linear equations, 2 equations, 4 unknowns. We could solve it with matrices. I don't think there's any need to. We can bring it to row echelon form in the equation form. What I do is subtract twice the first row from the second row, and that will give us this. 2x minus x is nothing, 5y minus 2y is y, and so on. And this is in echelon form already, and we can see that z and t are the free variables, and the dependent constrained variables are x and y. Let me also write that z and t are the free variables. And now we're going to use a technique of the wandering ones, I called it, where each time we let one of the free variables be 1 and the others 0.